Courses in the cement industry. Present to you.
If you look around any industrial facility, you'll see all sorts of rotating machinery. This equipment is important, so it's our job to keep it operating efficiently for as long as possible. Rather than dealing with each component separately, this program is going to cover a job that's common to most rotating machines: alignment. Let me back up a little bit to explain what I mean by alignment. Most rotating machines, like these for instance, are made up of two basic parts: a driver component, in this case a motor, and a driven component, in this case the generator. The two components are connected by a coupling. We perform an alignment in order to position the two components so that they rotate smoothly together. When two rotating shafts are coupled together in perfect alignment, they'll turn as if they were one shaft. That's the ideal situation, and it's very difficult to do. But the closer you can come to perfect alignment, the better it is for the machines and coupling. Even though most couplings are flexible enough to handle small amounts of misalignment, they'll last a lot longer if you approach perfect alignment. So what's perfect alignment? To understand that, I think it's easier to find the answer by asking the question in reverse. What's misalignment? Here's a drawing of a pump and a motor. I'll use it to explain what I mean by misalignment. Let's assume for now that the components are in perfect alignment. Now suppose we position the motor like this. We now have misalignment. It's called angular misalignment because one shaft is at an angle to the other. This, of course, is exaggerated, but it gives you the idea of what angular misalignment is. Let's remove the angular misalignment now so I can show you the other type you may find. Okay, now let's position the motor like this. What we have here is called parallel misalignment, or offset. The name comes from the fact that although the two shafts are parallel to one another, they are offset so that the centers of the shafts don't meet. For that reason, parallel misalignment is sometimes referred to as offset. Those are the two types of misalignment, angular and parallel. When no angular or parallel misalignment is present, you'll have perfect alignment. So the trick to an alignment job is to determine whether or not misalignment exists. Then you have to determine what type it is and correct it. Before we go on, let's review what we've covered so far. When two shafts in perfect alignment are coupled together, they'll turn smoothly. Angular misalignment exists when one shaft is at an angle to the other. Parallel misalignment exists when the two shafts are offset. Stop the tape now. Now that we know that two types of alignment exist, let's go a little deeper. Misalignment is measured in two planes, vertical and horizontal. Let's take them one at a time while I explain the difference. The drawing we're looking at shows the pump and motor from a side view. From this point, any misalignment found would be in the vertical plane. Let me show you what I mean. If we introduce some angular misalignment, it's caused by raising or lowering one end of the motor. This creates the angle between the shafts. So this is called vertical angular misalignment. Anytime one shaft is tilted up or down in relation to the other shaft, vertical angular misalignment exists. Let's realign the shaft and look at the other alignment problem that can occur in the vertical plane. When parallel misalignment occurs in this plane, it means that one shaft is simply higher than the other, like this, or lower than the other shaft, like this. So this is called vertical parallel misalignment. So when viewing machinery from the side, you can detect misalignment in the vertical plane. It could be angular or parallel. In a lot of cases, you'll find a combination of both. In other words, the shafts will be at an angle to one another and offset. The same problems can occur in the horizontal plane. Let me show you. Here's the same pump and motor combination. This time, however, we're looking at them from a top view. That way, we'll be able to see horizontal or side-to-side misalignments. If one shaft is shifted to create an angle like this, or like this, we have angular misalignment in the horizontal plane, or simply horizontal angular misalignment. Let's get back in alignment now and see the other type. If the whole motor is shifted one way, like this, or the other way, like this, we have horizontal parallel misalignment. And of course, you may find a combination of angular and parallel misalignment in the horizontal plane. If we put together everything we've seen so far, what have we learned? Well, there are two types of misalignment, angular and parallel. And there are two planes for misalignment to occur in, vertical and horizontal. So we end up with four types of misalignment to contend with: vertical angular, vertical parallel, horizontal angular, and horizontal parallel. And you may also find different combinations of the four types. Before you review this material with your instructor, I'd like to show you the four examples one more time. Stop the tape. we've identified that two types of misalignment exist, angular and parallel. And we also know that these misalignments can occur in two planes, vertical and horizontal. Now, I think the next step is to spend some time discussing the methods you'll use for detecting various misalignment conditions. Here's the pump and motor combination, and we're looking at them from a side view. Now, suppose we assume they're in perfect alignment right now. If the motor tilted like this, what type of misalignment would we have? If you're thinking vertical angular, you're right. Notice the angle that has formed between the two shafts when looking at them from a side view. One way of detecting this would be to measure the distance between the coupling halves at the top and at the bottom. If they're not equal, you have angular misalignment. In this case, the distance at the top is greater than the distance at the bottom. So we know we have a problem. There are a number of ways to make the measurement. A thickness gauge like this one can be used to get a pretty accurate reading. By fitting the gauge between the coupling halves, you can detect variations in the distance between them. There's a more accurate method, however, the dial indicator. The dial will give you a very accurate indication of any variations in distance between the two coupling halves. We'll spend a lot of time using it later on, so I won't go into detail at this point. What I do want you to remember now is that angular misalignment is detected by measuring variations in the distance between the coupling halves. In the example we saw, vertical angular was shown. Horizontal angular is detected in the same way, except you look for variations in distance from one side to the other rather than from top to bottom. How about parallel misalignment? Let's go back to a drawing while we discuss it. Once again, we're looking at the pump and motor from the side view. Now let's raise the whole motor to introduce some parallel misalignment in the vertical plane. How do we detect this? We measure the offset between the outer diameters of the two coupling halves. In other words, these distances indicate how much too high the motor is. The same measurement can be used to determine horizontal or side-to-side offset. How do you make this measurement? Well, one way to determine that some amount of offset exists is to use a straight edge. By placing the straight edge across the two coupling halves, a flashlight can be used to check for a gap indicating some offset. While that method will give you an indication of whether or not parallel misalignment exists, it's not a very accurate way of determining how much offset or misalignment you have. In a little while, you'll see how the dial indicator is used to make very accurate measurements of offset. But for now, just remember, parallel misalignment is detected by measuring offset between the two coupling halves. It can be measured top to bottom for vertical parallel and side to side for horizontal parallel. Let's review now. Angular misalignment is detected by measuring the distance between the coupling halves. Variations from top to bottom mean vertical angular. Side-to-side variations mean horizontal angular. Parallel misalignment can be detected by measuring the offset between the coupling halves. High or low offset means vertical parallel. Side-to-side offset means horizontal parallel. In the next segment, we'll look at the dial indicator in more detail. But for now, stop the tape. Now let's move on to discuss the dial indicator as an alignment instrument. As you know, the dial indicator uses a plunger to move the needle on the dial. Inward motion of the plunger causes a clockwise needle movement for an increased reading on the dial. Outward motion of the plunger causes counterclockwise needle movement for decreased reading on the dial. By properly mounting the dial on the shafts, you can use the motion of the plunger to measure misalignments. There's a lot to see concerning this procedure, and I think it'll be easier to understand if we watch an alignment job. We're going to pick up a job that has already progressed through some of the preliminary steps. Things like routine coupling maintenance and rough alignment using a feeler gauge and straight edge have already been done. It has also been verified that both shafts and couplings are round by using standard run-out procedures. Now you're ready to get started on the final alignment using dial indicators. There are several ways to mount the dials. The one I like to use involves an alignment kit. Let's look at a mock-up so you can see how it works. Think of these two pipes as the shafts of the machines we're aligning. The union between them represents a coupling. This kit allows you to mount the dials on the shaft rather than directly on the coupling. This has a couple of advantages. First of all, you don't have to be concerned with the many shapes and sizes of couplings. Secondly, you can bolt the coupling together so both shafts turn together when taking readings. Let's start over here. This post is rigidly mounted on one shaft. Because it's rigidly mounted, it will have the same angles and offsets as the shaft. The post is always installed on the shaft to which you will be aligning. The bracket is rigidly attached to the other shaft. The bracket is mounted on the shaft that is repositioned during alignment. So what we have is essentially the same setup we would have if we use the coupling. The only difference is that we're using the post and bracket to reflect shaft misalignment rather than the coupling to detect shaft misalignment. Any changes in the distances between the post and bracket show on these dial indicators attached to the suspended rod. On this one, the plunger will pick up changes caused by angular misalignment because it's resting against the face of the post. This one will pick up offsets because it's resting against the top of the post. That's the setup we'll be using during this program. Now, before you use the dials and brackets in whatever way you mount them, you should determine how much bracket sag you'll have. What's bracket sag? Let's look at the mock-up and I'll show you. Because the dial indicators are mounted on the end of the suspended rod, their weight will cause the rod to bend or sag a small amount. Even though it may only be a few thousandths of an inch, you should measure it so you can compensate for your readings during the alignment job. Every mounting will have its own amount of sag depending upon both how rigid it is and how long the dial indicator mounting rod is. So you should check and measure sag before each job. Let's see how it's done. Before you can select the equipment you'll be using, you should rotate the shaft and inspect it to determine the best place to mount the post and bracket. Once you know where they're going to be mounted, you can determine what size rod to use. When you're rotating it, check for keyways or any other obstructions that may limit the point where you can mount the post and bracket. Remember, we have to mount one on each shaft to span the coupling. Once a good spot is found, a rough measurement of the distance across the coupling is made. This doesn't have to be exact. It'll only be used to determine which rod to use. A measurement of the rod is made so we'll know which one will fit across this coupling. Now, rather than mount the post and bracket on the shaft at this point, a distance is measured off on a pipe that will indicate how far apart the two will be when they're mounted on the machine. That way, the whole dial indicator setup can be mounted on this pipe for the sag check. A pipe is used rather than the actual shaft because we want the dial indicators to only indicate sag. If we mounted them on the shafts, there might be some misalignment that would also show up. So by using a rigid straight pipe, the only deflections we'll see on the dial indicators will be the result of sag and not misalignment. Now, while he's installing the post, let's review. Dial indicators give accurate indications of misalignment. When properly mounted against an alignment post, two dials can be used to show parallel and angular misalignment. The rod attached to the bracket will sag slightly due to the weight of the dials. This sag must be determined so it can be compensated for in the alignment readings. Now, before we continue, review this material with your instructor. When we left the job, the technician was mounting the dial indicators on a pipe to measure the rod sag. Let's see how he's doing. Once the bracket and post are mounted on the pipe at the same distance they will be mounted on the shaft, the dial indicator rod can be installed. As you can see, it screws into the bracket. Then it's locked into position with a lock nut. The more rigid the mounting, the less sag you'll have, so make sure all fittings are good and tight. Now the first dial indicator can be installed. This one will be used to measure angular misalignment, so it's mounted against the face of the post. The second dial indicator will be used to measure parallel or offset misalignment, so it has to be mounted with the plunger resting on the top of the post. It's important to take the time to make sure that the dials are positioned properly and that they're good and rigid. Once mounted, the dials can be zeroed. A light tap on the mounting bracket will indicate that the mounting is rigid if the dial returns to 0 each time. The same is done with the dial mounted on the face. Slight taps will indicate if the mounting is secure. Because of the way they are mounted, the sag will only show up on the dial indicator mounted on the top. So that's the one to be concerned with. The indicator has moved backwards from 0 to 79 thousandths, which means it's a negative 21 thousandths. Sag should be read at maximum deflection and will always be a negative number. So the technician knows that 21 thousandths on the offset dial must be accounted for as sag and not misalignment. After checking the dial re-zeroed at the starting point, he double-checks the reading to make sure that it repeats, and it does. So now he knows that whatever reading he gets in the bottom position for offset alignment must be corrected for sag by 21 thousandths. The sag number is recorded on his data sheet to be used during computations later on. Now that he's determined the amount of rod sag, he can remove the dials and prepare to mount them on the shaft. The important thing to remember about sag is that it only affects the bottom parallel or offset readings. That's because the parallel dial is mounted in a way that causes the plunger to come out when the bracket sags. The outward movement is, of course, what accounts for the negative reading on the dial. Let's review now. Before the dials are installed on the shafts, they should be installed on a pipe or other rigid material to determine how much sag exists. Bracket sag only affects the bottom parallel alignment reading. So sag will be accounted for on that reading during the alignment job. Stop now and review dial indicator mountings and sag with your instructor. When we left the job, the technician had just completed a sag check on his mounting brackets. Remember, the amount of rod sag must be considered when taking the top to bottom parallel alignment reading. You'll see that in detail later on. Right now it's time to install the dial indicators on the pump and motor shafts. The alignment rig is installed on the actual machine pretty much the same way it was installed on the pipe for the sag check. The first piece to go on is the post. The post is mounted on the pump shaft because in this case the pump shaft cannot be repositioned. The motor is much easier to move around, so we'll be aligning the motor to the pump. When the post is up finger tight, it should be brought up snug using a wrench, or in this case, a socket extension. The idea is to get the post secure so that there's no unwanted movement. That way it will accurately indicate any misalignment on the shaft it's attached to. Next, the bracket is installed on the motor shaft. When installing the bracket, be careful to avoid keyways on the shaft. It could make the bracket wobble, giving you false indications. After the bracket is up finger tight, a socket wrench and extension can be used to snug it up. Both the bracket on this side and the post on the pump shaft must be rigid. A little shake will tell you whether or not you have a firm mounting. The next piece to go on is the rod that spans the coupling. You'll notice that the post and bracket are offset slightly. That's done in order to give you room to install the dials. The rod must be rigid too. It may take a little practice to get these dials on properly the first time. In any case, make sure you have the two dials resting securely in the proper positions. This dial will be used to measure angular misalignment, so its plunger will rest against the face of the post. Once the first dial is securely mounted against the face of the post, the second dial indicator can be mounted on the top of the post to indicate parallel misalignments. The dial should be resting securely on the post and be snug so that no unwanted movement occurs. Gentle tapping on both dials and the rod will indicate whether or not the fittings are rigid enough. Once the dials are mounted, the next step is to rotate the shaft to get the dials on top. Since we'll be taking readings around the shaft, it's a good idea to mark the shaft at 4 points. The bearing housing is usually a handy spot. The marks should be about 90 degrees apart. This is where all the data will be gathered, at each of these marks. It's not as important to get the marks exactly at 90 degrees apart as it is to ensure that you stop and take the readings exactly at your mark each time. Consistency in your collection points for information is what's really important. With these marks made, the technician zeroes the dial indicator for the parallel reading, and then zeroes the dial indicator for the angular reading. Touching one dial may cause the other dial needle to move, so be sure to double check that the dials are still at 0 when the adjustments are done. Once he has both dials set at 0, he can move on to the next step, which is to rotate the shaft one complete turn. The reason this is done is to make sure that the dials return to the 0 position when they're back at the starting point. That will be a good indication as to whether or not the mounting is rigid enough. If the dials don't return to 0 when they get back to the starting point, it means either that the shaft is moving along its axis due to thrust, or that the mounting isn't rigid enough. In our job, both dials return right to 0, so the technician knows that he has a good mounting for the dials. Now that the dials are installed, the technician can make some distance measurements that he'll need later on. You'll see how they're used later. For now, let me show you how our technician recorded those distance measurements. You can see them on the data sheet. Right below the sag of 21 thousandths, which was recorded earlier. First, he recorded the diameter of the circle scribed by the post. Then the distance from the post to the motor front feet and to the motor rear feet. Before we continue with the job, let's take a moment to recap what we've seen. The dial indicator brackets must be mounted securely to ensure a rigid fit. Any movement of the apparatus will throw off the readings later on. Once the dials are mounted, they are rotated to the top, so we have a starting point for all readings. The remaining reading points are marked 90 degrees apart so that the readings will be taken at the same spot each time. Finally, the shaft was rotated 360 degrees to check that the dials return to zero. If they don't, it will mean either a loose mounting or shaft movement. When we start to gather the initial readings, you'll see another way to make sure the indications are valid during the alignment job, but that's getting ahead of ourselves. Before we go on, stop and review this segment with your instructor. In the last segment, the technician installed the dial indicators on the pump and motor shafts. He also verified that the mounting brackets are rigid by rotating the shaft to see that the dials return to zero. Now, before he takes his first set of readings, there are a few more preliminary checks that can be made. One is called a soft foot check. This check is looking for an uneven footing on the motor, much like a wobbly chair with a short leg. Others include a piping strain check and cold to hot alignment considerations. A complete explanation of these checks is included in your text, so we won't dwell on them here. Let's get back to the job. The technician is about to gather his first set of readings. The first set is very important, so the technician double checks to make sure that both dial indicators are zeroed at the top. Then he carefully rotates the shaft so that the indicator post lines up with the first data collection mark. At this point, he'll record both dial indicator readings on his data sheet. He'll record on the outside of a circle the parallel dial reading, and on the inside of a circle the angular dial reading. The second position is read at the bottom. To read the dials in this position, an inspection mirror is handy. This may take a little practice since you're viewing a mirror image. He starts with the parallel dial reading and then checks the angular dial reading. When starting from zero, counterclockwise movement is a negative number and clockwise movement is a positive number. The last set of readings is taken after moving the shaft another 90 degrees. Remember, each time you rotate the shaft, it's very important that you take the readings at the marks you made. Once again, the inspection mirror is a handy way of reading the dials when they're facing away from you. He now has his final set of readings, And after they're recorded on the data sheet, he'll rotate the shaft back up to the starting position to make sure the dials come back to 0. If they do, he knows he has a valid set of readings, and they do. The next step is to analyze the readings. Let's take a moment now to review the readings the technician has recorded. Starting at the top, both the parallel and angular dials are at 0. Following the arrow, the first set of readings show positive 24 thousandths of an inch parallel and positive 9 thousandths of an inch angular. The second point has negative 10 thousandths of an inch parallel and negative 8 thousandths of an inch angular. The last set has negative 34 thousandths of an inch parallel and negative 17 thousandths of an inch angular. Finally, the dials return to 0 at the top. Now, to make sure the readings are valid, 2 checks can be made. The first one is that the dials return to 0 at the top, and they have. The second one involves a little arithmetic. Let me show you. The sum of the top and bottom readings should equal the sum of the left and right readings. This applies to both the parallel readings recorded outside the circle and the angular readings recorded inside the circle. Let's check it out. Starting with parallel, the top to bottom sum is 0, negative 10, or negative 10 thousandths of an inch. The side to side is positive 24, negative 34, or negative 10 thousandths of an inch. So the parallel readings are valid. Now how about angular? The top to bottom sum is 0, negative 8, or negative 8 thousandths of an inch. The side to side is positive 9, negative 17, or negative 8 thousandths of an inch. So the angular readings also check out. We now have the information we need to start calculating movements to correct misalignment. But before we do that, stop and review this segment. Up to this point, we've gathered an initial set of readings, and we've determined that they're valid. The next step is to put the readings in a usable form and also to correct for rod sag. Let's look at the data sheet while I explain how these things are done. To correct for bracket sag, the sag amount is subtracted from the bottom parallel reading. The remainder will be the actual deflection due to misalignment only. Then, to make the readings easier to interpret, it's a good idea to make as many readings relative to 0 as possible. We already have zeros for the top to bottom readings. Now we'll convert the side to side readings to be relative to 0. It's done by adding the side to side readings together, like 24 plus 34 equals 58. The 58 goes on the side of the largest number, in this case where the 34 was. And the sign of the largest number, negative in our example, is given to the new number. So the result is negative 58. which of course means negative 58 thousandths of an inch. What does this mean? Well, it means that the dial moved a total of 58 thousandths of an inch in the negative direction from here to here. So it's the same as calling the starting point 0 and the other side negative 58. Don't try to memorize the math right now. You'll see more examples in the text. Just remember that it should be done to clarify what kinds of misalignment you have. Okay, let's rejoin the technician now as he computes his readings. This is the technician's data sheet with all the measurements and recordings he's made up to this point. The first step will be to subtract the sag from the bottom parallel reading. Negative 10 minus a negative 21 equals a positive 11. Next, he converts the side-to-side readings to zeros and comes up with a negative 58. The negative sign was the sign of the 34, so it's used. The angular readings end up at negative 26. And the bottom readings remain the same since the top started at 0. The next step is to begin calculating shim changes and movements to correct misalignments. The way this is done is to visualize the position of the driver shaft in relation to the driven shaft for each of the types of misalignment that can occur. All misalignments in the vertical plane will require shim changes to correct. Misalignments in the horizontal plane call for lateral shifts of the motor to correct. It's best to start with vertical adjustments in case the lifting of the machine causes a lateral shift. When all vertical moves are done, the motor can be moved on the shims to correct horizontal problems. So let's start by analyzing the vertical angular problems. Looking at the data sheet, we see that the angular dial went from 0 to negative 8 thousandths of an inch from top to bottom. What does that mean? Let's look at a sketch to see. Since the angular dial moved from 0 to negative 8 thousandths of an inch from top to bottom, the motor shaft must have moved away from the pump shaft by 8 thousandths of an inch. So the exaggerated view of the two shafts from the side is like this, an obvious angular problem. If the angular dial has moved in the positive direction, it would indicate that the motor shaft was moving toward the pump shaft at the bottom. In any case, angular misalignment exists. So how do you correct it? In the next segment, we'll see how. But before that, let's review. Correcting all measurements so that they are compared to 0 makes visualizing alignment problems easier. Analyzing the new numbers will tell you what's occurring. Negative dial movement means the motor shaft is moving away from the pump shaft at the bottom. Positive dial movement means the motor shaft is moving toward the pump shaft at the bottom. We'll do a similar analysis of the dial movement for the rest of the reading. But for now, stop and review. You'll recall that when we left the technician, he was about to begin calculating his first move to correct misalignment. As you know, it's best to start with vertical correction first. So let's see how he figures out the vertical angular movement. Calculation begins by drawing a sketch of the relationship between the pump and the motor. So that he's not confused, he labels the sketch as a vertical angular. And of course, all vertical readings are measured by looking at a side view. The sketch shows the pump and the pump shaft. The pump will remain in position while the motor is moved in the alignment. The motor is drawn, showing an exaggeration of the angular misalignment discovered by the negative 0.008 of an inch reading on the dial when it was at the bottom. The dotted line labeled A shows where he wants the shaft to be. And B, of course, is the amount of misalignment already measured. Another dotted line shows where the rest of the motor and shaft should come to. The dotted line labeled F is the location of the front feet, and the dotted line labeled R is the rear feet of the motor. Next, we'll have to record the distances to the feet from the post. The distance from the dial post to the front feet is 24 inches, and he labels it C. The distance to the rear feet is 40 inches, and he labels it D. He now has all the information he needs to make the calculation for movement. A formula to determine what must be done to the front feet is now used. The front feet movement is equal to B divided by A times C. Before we continue, let me say that the basis for the formula is pretty complex, so we won't dwell on it here. An explanation of the formula is covered in your text. For now, just watch how it's used to calculate shim changes. Now, B, of course, was the amount of misalignment measured, and that was 0.008 of an inch. A was the diameter of the post that he measured earlier. It was 13 inches, and C is the distance to the front feet, which is 24 inches. The result of this equation will be how much movement or change must be made to the front feet. A calculator can be handy to make the computation. He clears it before starting. The answer is 15 thousandths. That means that the front feet must be lowered by 15 thousandths in order to get the motor shaft in alignment with the pump shaft. So shims totaling 15 thousandths must be removed from the front feet. Now, you can't just remove shims from the front feet. You also have to remove some shims from the rear feet in order to keep the motor level. The equation for the rear feet is the same. R for rear equals B over A times D. This time the distance to the rear feet. This alignment is again 8 thousandths divided by 13 times 40. So essentially it's the same equation, except that we use the distance to the rear feet, which was 40 inches in this instance. Calculation in this case comes out to 24 thousandths of an inch. So 24 thousandths must be removed from the rear feet. He now knows what must be done to correct the vertical angular misalignment. So by using a simple formula, the technician was able to calculate the required shim changes to both front and rear feet in order to level the motor and correct the vertical angular misalignment. Now you'll see the formula again in your text, but let me review it for you here before we go on. Assuming we're calculating front feet shim changes, which we call F, we'll need to know the diameter of the dial post, which we call A. The amount of vertical angular misalignment, which we call B, and the distance from the dial post to the front feet, which we call C. The formula is then F equals B divided by A times C. The same basic calculation is done for the rear feet, except we use the distance to the rear feet in the formula instead. Once you've made the calculations, you can correct the problem. The appropriate shim thickness is removed from each foot. Then, after retightening all the feet, another set of readings is taken. The readings are recorded on a data sheet so that the next calculation can be done. If you're careful to loosen only one foot at a time, you'll avoid upsetting the rest of the readings. When you take the new set of readings, you'll know if this has occurred. You'll also know whether or not the shim change has corrected the problem. If you're not within specifications after the move, you'll have to calculate any additional shim changes in the same way as the first one. Once you've satisfactorily corrected the vertical angular problem, you can move on to the vertical parallel misalignment. This one is calculated in a different manner. Let's watch. This is the data sheet showing the readings taken after the vertical angular alignment correction was made. You'll notice that the vertical angular is now down to a negative 1/1000th, which is well within specifications for this machine. The vertical parallel, on the other hand, shows an 11/1000th offset. Because it's positive, it means that the motor is 11/1000ths of an inch higher than the pump. The shim change to correct an offset or parallel misalignment problem is equal to the total offset divided by 2. This rule applies to any parallel misalignment problem, whether it be vertical or horizontal. In this case, the total offset or amount of misalignment was 11/1000ths. So the shim change to correct this would be 11/1000ths divided by 2. This turns out to be 5 1/2 thousandths, or 55 10,000ths. The technician in this case rounds the number up to 6 thousandths. And this 6 thousandths must be removed from all 4 feet of the motor to lower it into alignment with the pump. To complete the alignment job, similar techniques are used to calculate horizontal, angular, and parallel shifts. Use the same formulas, but this time consider the side-to-side misalignments when viewed from the top. Then you'll know how much to slide the machine and in what direction. Examples of all these calculations are in your text for review purposes. After the shift is made to correct the horizontal offset, a final set of readings should be taken to assure good alignment. Whenever aligning components, always think before you act. Then you'll save time and avoid unnecessary moves. This training program has been general in nature. When performing any mechanical maintenance in your plant, be sure to follow the specific maintenance and safety procedures provided by your facility and the equipment manufacturer. If you have any further questions, talk to your instructor or your job supervisor. And always use the best safety practices when doing any work.
Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.